All right, let's go ahead and get started. Greetings, everyone, in whatever respective time zone you may be in. Good morning to everyone in the Eastern time zone. Welcome to Inotherm, MIT's International Colloquia on Thermal Innovations. Today, we're going to have our 25th colloquium with a talk by Professor Ken Sandhage from Purdue University. The talk is going to be on materials alchemy, shape-preserving chemical transformations for generating 3D structures for thermal, chemical, and optical applications. I'm Professor Ashegun Henry, professor at MIT in mechanical engineering. I'll be introducing the speaker and helping to moderate questions at the end. Just as a quick overview, we're going to have approximately 50-minute or so presentation, and then roughly 20 minutes or so of question and answer, and then a wrap up at the end. If you have questions, if you have things you want to ask, please use the Q&A button. We'll be pulling questions from the stream of Q&A entries, and I'll ask the questions to the speaker. And if you have questions, if you want your questions to remain anonymous, you can indicate that. You can use the anonymous feature. We will generally post these colloquia on YouTube afterwards so that people can see. So if you have questions that don't get addressed today, you can follow up with the speaker. And sometimes there's also discussions under the YouTube links as well. Just as a note, our next colloquium, next webinar is going to be from Professor Dennis White at MIT on fusion reactor first wall cooling. And just as a wrap up, we'll come back to this at the end, but please type your suggestions for any future events or future topics, future speakers in the Q&A. Let us know what other topics you'd like to see included, and you're strongly encouraged to sign up on the email list. You can see all the past videos and Q&A all on our website, inotherm.mit.edu. So now for Ken, our speaker today, I'm highly honored to be able to introduce Ken. Ken is the Reilly Professor of Materials Engineering at Purdue. He did his bachelor's in metallurgical engineering at Purdue and his PhD in ceramics at MIT. He was one of the first employees at American Superconductor. It's the company that was founded by his advisor, Greg Urich. And American Superconductor pioneered the use of superconducting transmission wires. And Ken has really continued the tradition of his academic lineage of making very real, tangible, commercializable, clever solutions to hard engineering problems. After working in industry for about 5 years as a senior scientist at Corning and American Superconductor, he joined the material science and engineering department at Ohio State. And then in 2003, he moved to the School of Material Science and Engineering at Georgia Tech, where he was the B. Mifflin Hood Professor. And then in 2015, he moved to Materials Engineering at Purdue. Ken has made immense contributions to the field of heat transfer through his materials innovations. Most notably, he pioneered the development of a clever shape-preserving reaction-based process for generating materials with tailored chemistries and micro to nanostructures. He'll talk about it today, but from my perspective, to me, what's so remarkable about the process that he's developed is that he can take materials that would be extremely hard to form, materials that are very refractory. They can work at extremely high temperatures. And because of that, they're very hard, and they're very difficult to machine, even with something like diamond tooling. And he can take those kinds of materials and make them into extremely complicated shapes very easily. And so he'll show you more about this in his talk. But I just wanted to note that, comment and remark that his innovations have really broad implications for heat transfer. Applications in energy, transportation, defense, environmental, and even medical applications. And Ken also gives really great talks. So very excited and pleased to have him speak today. I think you'll find his work very, very interesting. So Ken, why don't you go ahead and share your screen and take it away.
Okay, actually, can you see the screen okay?
Yep, looks great. Thank you.
Okay, thanks, Professor Henry, for the kind introduction, as Ashay, and for the opportunity to present this work today to this international audience. I'll be talking today, as Professor Henry mentioned, on our approaches for generating chemically tailored, complicated three-dimensional structures for a host of potential applications, not the least of which are thermal, but also chemical and optical applications as well. And so what you see on the front page here, front slide, are two examples of this. On the left are solid fuel rocket nozzle liners made of a composite that's going to sound exotic, but we actually picked it for particular reasons for this application, zirconium carbide and tungsten. On the right, you see an example of a channeled heat exchanger plate. And this is actually for a printed circuit type heat exchanger for concentrated solar power or other applications. And as you can see on the lower left corner of that image, what we have is a co-continuous, fully dense ceramic metal composite of this material, ZRC tungsten. And so the philosophy that we have, albeit somewhat perhaps exotically entitled materials alchemy, is to separate the two processes that are involved in making these kinds of materials. Separate the shape forming process to allow for conventional, scalable, easy shape forming techniques from the chemical tailoring process to convert those shapes into desired materials. And by doing that, that gives us a lot more flexibility in the chemistries and in the shapes we can produce. I should say we're not limited to these macro scale, microstructured components, but also to microscale nanostructured components, including those conveniently provided to us by nature. And so on the left two images here, you see chemically modified shape-preserved structures originating from diatoms. If you're not familiar, diatoms are a type of microscopic single-celled algae that are incredibly remarkable in their ability to make silica in almost any shape you can imagine and more. And so we've learned how to take those silica shapes and convert them into a host of different materials, including silicon, as you see on the left, for a number of applications, including batteries. And on the image second from the left, where we've converted a particular diatom silica microshell into a gold replica for an optical application. We've also developed strategies taking bioorganic templates and tailoring them. And so you see the red image there of a europium barium titanate photoluminescent butterfly scale from the butterfly Papilio bloomii for an anti-counterfeiting application. Clever idea from one of the grad students in my group. And on the right is a pollen particle, sunflower pollen, that we've modified to make magnetic, to have multimodal adhesion capabilities for a Navy project. And so let me then tell you how we do this and explain to you why I'm calling this materials alchemy. If you look at the etymology of the word alchemy in an unabridged dictionary like Webster's, the first definition that pops up from Arabic and Latin and Greek roots is the medieval chemical science and speculative philosophy whose aims were, and most commonly recognized definition, is the transmutation of base metals into gold. But interestingly also the discovery of a universal cure for disease and the discovery of a means of indefinitely prolonging life. On the right side, you see a painting from the 1700s of a supposed alchemist searching for what's called the philosopher's stone, which is supposedly a material that can convert base metals into gold. Of course, we're not doing this exactly. If you look at the second definition in the Webster's dictionary, it says magical power of transmutation. I wouldn't say what we're doing is exactly magical. But if you look up the word transmute as a key part of the word alchemy, it means to change into another substance or element. So the philosophy we have is to learn how to make shapes and then convert them without changing their features, their shape features, or even their dimensions, to make them have the right combination of shape and chemistry for the applications that we want to pursue. So I've been blessed to have a number of really hardworking and clever graduate students, former and current, in my time doing this sort of work, a number of hardworking postdocs and research scientists who also deserve every bit of the credit that I'll be talking about, what successes we've had to date. And a particularly important aspect of this is the collaborations that we've enjoyed from a number of different universities, national labs, and companies. And Professor Henry has been a really wonderful collaborator and really got my group into this field of concentrated solar power, which I really hadn't known much about until he happened to knock on my door one day when we were both at Georgia Tech, and then it really took off from there. So how do we do this? How do we change chemistry but not shape? We've actually developed a couple different strategies for this. One involves the use of fluid-solid reactions of different types, whether there be displacement, additive, or subtractive reactions. And we've done this both on macroscale templates that are microstructured and microscale templates that are nanostructured. With the macroscale templates, we've tended to use liquids as the reactive fluid, so liquid-solid reactions. On the microscale, gases as the reactive fluid, because gases can generally penetrate smaller spaces, such as nanoporous materials. We've also developed strategies involving conformal codings. Now, I should confess that in this case, the replication we do is actually negative. In the case above, we're making positive replicas from a starting material. In the cases below on conformal coding, they're actually negative replicas. We're putting highly conformal coatings on a complicated shaped template and then removing the template. So the coating is where there wasn't anything previously, so it's really a negative coating. But if the coating is conformal and thin, it appears as though it's a positive replica. And so I'll show you how we've done this both on inorganic and organic templates using a solid gel-based technique. And we've also used a protein-based technique and electroless metal deposition. I won't go through all of these, but I'll give you kind of snapshots of the approaches and how we have pursued them. So let me start with the top one, macroscale, microstructured templates with liquid-solid reactions. So when you think about thermal applications and extreme thermal applications, it doesn't get much more extreme than for solid fuel rocket nozzles. So on the back end of a solid fuel rocket where the nozzle exists, the temperatures can soar from ambient to over 2,500 C within a second, extremely thermal shock prone. What's more common, a common type of propellant, solid fuel propellant, is aluminum powder mixed in with organic matrix. And so you ignite the aluminum, it oxidizes, gives off enormous heat, burns the organic, and the aluminum oxide liquid and the gas products that travel through the nozzle will do so at hypersonic speeds, over Mach 7. So it's extremely erosive. And so the materials that you need for this, you can pretty much count on your hand that are used now for this, because they need to be very high melting, extremely thermal shock resistant, erosion resistant. Of course, you'd like them to be lightweight since you're launching the missile. Non-porous, meaning that you want the propellant, the combustion products to go through the nozzle orifice and not through the sidewalls of the nozzle. And of course, inexpensive, and the materials you use and how you fabricate it. And so these are difficult combinations of properties to satisfy at the same time. And in particular, erosion resistance is challenging. As I mentioned, the common materials that are used for this are tungsten or tungsten alloys because they're so high melting, and carbon-based composites. Certainly carbon's quite lightweight, but it is not very erosion resistant. And even tungsten alloys are not terribly erosion resistant, particularly erosion resistant at these really high temperatures. And both types of materials are not inexpensive to make for rocket nozzle applications, even the carbon-containing ones, because of the need to make them fully dense. So how can you choose materials and choose techniques for making them that will satisfy these complicated combinations of conditions? Well, we focused on a CERMET, and a particular one that has combinations of properties we think are particularly well suited for this application, tungsten and zirconium carbide. So tungsten is the highest melting metal. Zirconium carbide is also quite high melting. And when you put them together, the solidus temperature, that is the onset of melting, is still quite high, 2,800 centigrade. If you look at the tungsten zirconium carbide carbon phase diagram shown there, you can see the arrow pointing to the solidus temperature of 2,800 C. These two phases are also chemically compatible. They form a tie line. But importantly, they have some limited solid solubility in each other. That's important. I'll talk about this later when I mention diffusion bonding of these types of ceramides to each other. What is particularly remarkable, and particularly why we picked this combination, is that they overcome an Achilles heel of ceramic metal composites, and that's the difference in thermal expansion. The coefficients of thermal expansion between tungsten and zirconium carbide are quite close from room temperature, 4 to 4.5 times 10 to the minus 6 per degree C, and as high as it's been measured, 2,700 C, from about 9 to 10 times 10 to the minus 6 per degree C. That is remarkably close, actually, because most ceramides, the metal expands and contracts a lot more than the ceramic does, and that leads to internal stresses and failure. So that's not a problem we suffer from here. What's more, both phases, tungsten and ZRC, are quite thermally conductive, which is important for heat exchanger or for applications or for just removing heat from a hot base. They're mechanically compatible. That is to say, the carbide provides the hardness and erosion resistance that you need for this application at high temperatures. Tungsten becomes ductile on or about 300 C, and so the composite is tougher than zirconium carbide by itself, and certainly more erosion resistant than tungsten by itself. Of course, if you're launching something, you want it to be as light as possible. Tungsten is, of course, quite heavy, 19.3 grams per cubic centimeter. As much tungsten as you can replace by ZRC, the better off you are for achieving a lighter weight material to launch. So we think this combination of properties, as exotic as the Ceramet sounds, are really well suited for this particular application. And like I said, we searched for this combination. It wasn't by accident that we picked it. What's more, we have a technique for making these things in complicated shapes, which is the main emphasis of the talk today. How do you make a shape and how do you convert it into the chemistry that you want? So the process we've invented is called the displacive compensation of porosity. That's a mouthful. I'll explain what that means in a second, or DCP process for short. We have a number of patents and a number of active patent applications on this approach for certain applications in particular. So how do you make a complicated shaped ZRC tungsten Ceramet? Well, we start with porous tungsten carbide that we can form in a variety of ways using low-cost techniques that I'll show you shortly. We take that porous tungsten carbide preformed shape and we expose it to a zirconium-containing liquid. The zirconium in the liquid goes after carbon to form ZRC and tungsten. It's a displacement reaction. The carbon is displaced from tungsten carbide to ZRC and liberating tungsten in the process. This is a quite thermodynamically favored reaction over a wide range of temperatures. ZRC is a much more stable carbide than is tungsten carbide. What's more, the carbide we produce has a larger volume than the carbide we consume. And even more important, the combination of the two solids we produce, ZRC and tungsten, is about twice the volume of the starting tungsten carbide. So that's how we do the conduct the shape preservation. If we start with a 50% porous preform, you can fill the pores in with the ZRC and tungsten solid products and not have a significant change in shape or dimensions, less than 1% dimension change. That's the idea. We call it DCT because we're using a displacement reaction to compensate for the prior pore space in the preform. Now, we don't usually use pure zirconium as the liquid because of its high melting point. Instead, we alloy the zirconium with a solvent, copper, which substantially lowers the melting point. In the case of ZR2Cu, a congruently melting intermetallic, down to 1,000 degrees C, which is a much more manageable temperature for doing these reactive infiltration experiments. And to show you what I mean, here's the copper zirconium phase diagram. Zirconium melts around 1855 C. If you add just 1/3 copper, you can form the ZR2Cu congruently melting intermetallic at 1,000 degrees C, which from a furnace technology standpoint is a much more manageable temperature than 1855 C. What's more, copper is inert with respect to zirconium carbide and with respect to tungsten. Here's the copper-tungsten binary constitution phase diagram. Probably the most boring phase diagram you'll ever see. They don't form any compounds together, very limited solubility in each other. And what's more, the melting point of tungsten, 3422C, hardly changes in the presence of copper, 3414C. And I suspect much of that difference could be the error of the pyrometer used to make these measurements. So it's a very negligible interaction of copper with tungsten as well. So it's an excellent solvent for this application. So in terms of an illustration of how this process works, we start with a porous tungsten carbide preform, which I idealistically show as the spheres that are connected together. We dunk the preform in a zirconium copper liquid. It pressureless infiltrates like water into a sponge, and then we allow the reaction to happen. And so the zirconium goes after the carbon in WC, and actually you form layers as shown here, a layer of tungsten around the tungsten carbide as it's reacting, and a layer of ZRC around that. And the process continues until the pores are filled because of the doubling of internal solid volume due to this internal reaction. And so it's a process that allows us to make dense, net-shaped parts without the common problem of shrinkage. You can certainly make ZRC tungsten composites by mixing the powders and sintering them, but then in that case, the whole part collapses to fill the pore space, and it's difficult to make complicated shape, distortion-free parts that way, as opposed to this approach. So we can densify with that. We made by CNC machining, green machining. Here's what the same sample looks like after we've done the dunk at 1150 C for 30 minutes and then pulled it out and reacted it further at 1300 C. You can see some of the copper that didn't completely drip off. We etch that external copper away with nitric acid, dilute nitric acid, and we can make the final dense part. Again, these are all the same part at different stages of the process. So we measure the dimensions, the large diameter on the bottom, the smaller diameter on the top, and the height, and it hardly changes. And so the tungsten carbide preform, the large diameter was 50.65 millimeters, and went to 50.32 millimeters. Typically, we get about a 0.5% shrinkage. That's 300 microns difference between those diameters, not much at all. We've done other shapes as well. In this case, we green machined a cone and converted it, again, very small dimension changes. from this process. If you cross-section the material, it looks like this at low magnification in the SEM. I should mention these are very difficult materials to cut. If you try to cut this with a diamond blade, wafering blade, it takes a long time. Fortunately, however, these materials are also electrically conductive. And so we typically cut these materials by electrodischarge machining and then polish them. And so what you see here is a polished low magnification cross-section. You can see a few pores, but not much. Some of that may be pull out from polishing. If you zoom in, you can see the dense zirconium carbide bearing matrix and the brighter tungsten particles. A pretty homogeneous distribution of both phases. So we went from a 50% porous preform to a fully dense part, and again, the dimension changes are less than 1% typically. So we can also quantify the phase content and the relative porosity by using techniques like quantitative X-ray diffraction. On the left, you see a typical X-ray copper K alpha X-ray diffraction pattern for such a ceramite. You see the two product phase peaks, ZRC and tungsten, as well as some residual tungsten carbide and some residual copper in the sample. And so to quantify the phase content, we can actually, in advance, pre-mix known amounts of ZR2Cu tungsten carbide in the products for, say, 10% reaction, 20% reaction, 90% reaction, and pre-X-ray those known amounts to generate a calibration curve. And so if we compare the area under the 110 tungsten peak to the 100 tungsten carbide peak, tungsten's a product, tungsten carbide's a reactant, we can get the extent of reaction from X-ray diffraction analysis. And so what you see on the left there is the typical extent of reaction. Something like 95% is typical for us. And so the reaction below is the overall reaction. So zirconium copper liquid goes in, the tungsten carbide, it forms ZRC, it forms tungsten. We may have some residual tungsten carbide that didn't react. We may have some residual copper that didn't leave, a solid, and the copper that left. And so if we can determine those two parameters in that reaction A and B, we can unambiguously determine the phase content. And so A, we get from quantitative X-ray diffraction analysis by looking at the tungsten to tungsten carbide ratio, as I mentioned. If we measure the mass change, we know from the reaction what contributes to the mass change. We can determine B, and from those two parameters, we can determine unambiguously the phase content, which is typically around 58 volume percent ZRC, about 36 volume percent tungsten. They're both interconnected phases, and smaller amounts of residual tungsten carbide and copper. Since we have the phase content, we can determine the theoretical density from real mixtures and then compare that to the bulk density. And we typically get about 2 or 3% porosity or 97% dense. And that also compares similarly to the porosity we see from image analyses, which gives us pretty good confidence that we have the right porosity value. And so we know that these materials are quite dense, and we know their phase content using these techniques. So we've also used gel casting. We worked with a company to develop a gel casting process to make a rocket nozzle preform liner. This is a porous tungsten carbide preform after gel casting, burning out the organic and light sintering to make a 50% porous rigid preform. And then we converted that into a rocket nozzle liner using our DCP process. And again, the diameter change here was less than 1%. So there's nothing like a real test to prove whether this is going to work in this application. So we were fortunate to be able to work with Wes Hoffman at Edwards Air Force Base. Wes took our rocket nozzle liner and surrounded it with a carbon composite. He did that because in the test that it's upside down relative to a rocket. The propellant's on the bottom, the nozzle's on top. It's a nozzle liner, and so he wanted to make sure that the propellant went through the orifice and not around it, so he backed it with carbon just to fill space. And then he conducted the test using an R45M propellant, a Pi K rocket test. It has a fairly high aluminum content, so it's fairly erosive. And when Wes pulled it off, he saw no evidence of erosion from this material. And so this is a very thermal shock resistant, erosion resistant ceramite that survives that kind of an extreme condition. So a second application area for this kind of material is one, as I mentioned, that Professor Henry really helped us understand and develop materials for, and that's concentrated solar power. This is an artist rendering of the power tower concept of CSP. The idea is it's sort of the other type of solar power. Most of us are very familiar with photovoltaic solar energy, electricity generation. This is a different approach. You have a field of heliostats, mirrors that focus the sunlight to the top of a tower where there's a receiver, and the heat from sunlight is ultimately used to create electricity. And so a more detailed drawing is shown here. So the heliostats will focus heat to the top of a tower or to a receiver. There are different media that can be heated, such as solid particles that can flow down as a curtain, or molten salt. And this is the molten salt paradigm. So the idea is the salt comes up the tower colder, gets heated up by sunlight to be hotter. You can store that salt in a tank. So these systems can run 24 hours a day, 7 days a week, even when the sun isn't shining. by using the heat stored in the tank at night. When you want to create electricity, that hot molten solid can be passed through a heat exchanger to transfer heat to a working fluid, steam or supercritical carbon dioxide. That working fluid can expand, spin a turbine connected to a generator to create electricity. And so to get this type of an approach to be more cost effective, to reach parity on cost for electricity with fossil fuel derived electricity, one of the key steps that has to happen is to get the system to operate at a higher temperature, to be more efficient in converting sunlight, heat into electricity. And so one of the challenges in doing that is the heat exchanger that's used for this type of a process. So as I mentioned, prior authors from MIT, in fact, have shown nicely in a number of papers that by increasing the turbine inlet temperature in this type of a turbine application, the efficiency converting heat into electricity can be significantly improved. What you see here are two curves, different working fluids, supercritical CO2 or helium, different locations for the curves, but the trend is the same. As you go up in temperature, the efficiency goes up. Currently, CSP plants operate at highest temperatures around 550 or so centigrade. We'd love to get up to 750, 800 or higher to get a dramatic increase in electricity efficiency production and lower effective levelized cost of electricity. So one of the challenges in doing that is the heat exchanger. A very effective type of heat exchanger, compact heat exchanger, is called a printed circuit heat exchanger. They're currently made out of metal alloys like stainless steels, and you can see some of the photographs of this type of heat exchanger. They're very thin sheets of metal that have been patterned into channel patterns, as you see on the upper right there, typically by a chemical etching process, which itself is kind of slow and somewhat expensive. But even beyond that, the challenge in doing this with metal alloys and using them at temperatures like 750, 800 C is the fact that the mechanical properties of the alloys start to degrade at these high temperatures. This is a plot obtained from the ASME boiler pressure vessel code. It was compiled by Mark Anderson at Wisconsin. If you plot the maximum allowed stress for a number of alloys versus temperature, for high pressure applications like in the use of supercritical CO2 as a working fluid, this plot shows a number of alloys, stainless steels, and a variety of nickel-based alloys. And while they have a nice set of properties below, say, 500 or so, for all these alloys, above 550 or 600, the mechanical properties really degrade. That is, especially the creep rupture life. So that by the time you get to 800 C, the maximum allowed stresses, according to the boiler pressure vessel code, are only on the order of 5,000 PSI or less, which is dangerously close to the operational pressures that one would like to use the supercritical CO2 at. So that's what drove Professor Henry and myself to look at other alternative materials, such as zirconium carbide tungsten. So as you'll see shortly, we were able to form channeled plates of this material, not by etching, but by mechanical forming of the tungsten carbide, convert the porous plate into a dense one of ZRC tungsten by the DCP process, and then diffusion bond the plates together to make a stack. These materials are stiffer, they're stronger, and they're more thermally conductive than the metal alloys I just described. And Professor Henry and I have a patent application on this. So, in fact, that led to a first project from DOE on making robust ceramic metal composites that involved my group, Professor Henry's group at the time. He was at Georgia Tech, as I was when we first got this, Oak Ridge National Laboratory, and University of Wisconsin. So just to remind you, even for this application, ZRC tungsten has attractive characteristics. Again, it's high melting, well above the solid temperatures of stainless steels and nickel-based superalloys, which are typically 13 to 1400 C or so. They're stiffer and stronger at 800 C. And so as you'll see, we measured the failure strength of these materials at 800 C, and it's about 87,000 PSI. And so just to put that in perspective, here's again the ASME boiler pressure vessel. And I have to say that these two materials, the metal alloys and ZRC tungsten, fail in different ways. ZRC tungsten fails by fracture as opposed to predominantly creep rupture for metal alloys. But the point is, the failure strengths are dramatically different. For the metal alloys, as I mentioned, you're looking at 5,000 PSI or so at 800 C. Our material is on the order of 87,000, way off the chart here. And so we think it has strong potential for that reason from its mechanical perspective. But it's also tougher than monolithic ceramics. As I mentioned, tungsten at elevated temperatures provides ductility. The toughness of the ceramite, in fact, has been measured to be about 9.4 MPa root meters. To just put that in perspective, that's more than about 0.8 for relatively tough Pyrex glass, 1.4 for concrete, and about 5 for silicon carbide. In fact, we've done poor man toughness test, we can drop these things from a meter and they just bounce basically. So they're really quite tough cermets. As I mentioned, they're also thermal expansion match, which is good for a cycling application like heat exchangers. And they're quite thermally conductive. We've measured the thermal conductivity at 800 C to be about 66 watts per meter Kelvin, which is something like 2 or 3 times higher than for stainless steels or nickel-based superalloys, which is kind of a nice characteristic to have, of course, for a heat exchanger. So because of these thermal characteristics, they're quite thermal shock resistant. I've already shown you that already with a pi-K rocket test. But even with more modest heating, 10 degrees a minute from room temperature at 800 C, and then measuring mechanical properties afterwards, we've not seen a degradation in fracture strength after such cycling. I don't have time to get into it today, unfortunately. I'm happy to talk to you about it if you're interested. But we've also learned how to tailor the surface of ZRC tungsten and of the supercritical CO2 working fluid so that they're resistant to corrosion, even after 1,000 hours at 750 C at 20 MPa in the supercritical CO2-based fluid. And we have an application on how to do that too. And finally, of course, we have for this application a cost-effective way to make the heat exchanger plates by forming channeled preformed plates and then converting them through the DCP process to assemble the heat exchanger. And Professor Henry and I have a patent application on this. So we measured the mechanical properties at elevated temperatures. This is in collaboration with Michael Sandhage, Professor Sandhage's group here at Purdue. He has a 4-point bend testing capability that we've utilized as per the ASTM standards. We made configuration A bend test bars that were diamond grounded and chamfered again as per standards. And what we found was that the fracture strengths, mean fracture strengths at room temperature are about 700 MPa, about 100,000 KSI, and at 800 C, about 600 MPa, or about 87,000 PSI. So unlike stainless steels or nickel-based alloys where the failure strength dramatically drops when you go up in temperature, we retain 85% of the failure strength of these materials at 800 C. The thermal conductivity is also quite attractive. We went to the Edward Orton Ceramic Foundation, had them measure the thermal diffusivity and the heat capacity using laser flash and differential scanning calorimetry, respectively. You can use those two numbers, of course, to calculate thermal conductivity, which turns out to be 66 watts per meter Kelvin, and again, 2 to 3 times higher than for conventional stainless steels or nickel-based superalloys that are used in printed circuit heat exchangers. So the idea is to make plates of porous tungsten carbide with channels, as well as flat plates, and then convert them into dense ZRC tungsten plates. And so one way to do that is to simply compact powder into a plate shape and then green machine it, as I showed you earlier. We've done that. We actually have a CNC milling machine at Purdue to do this. And this is what it looks like. This material of the machine is quite readily because it's 50% porous, quite friable, with standard carbide tooling. However, I think a better way to do this is simply stamping. And so we've made much thinner plates with rather complicated, simple and complicated channel patterns by simply stamping these patterns into the powder, as well as having channel vias for vertical fluid transport as well. And it is, if you fracture this, it's made of 5 to 6 micron particle size tungsten carbide, about 50% porous, and it is, of course, WC by X-ray diffraction analysis. So then we take plates like that and we undergo the DCP process with a rack melted filtration. There's an example of one such plate. Again, it retained its shape and dimensions to within 1%, and the microstructure on the right shows that it's fully dense. Again, gray ZRC tungsten-based matrix and brighter tungsten-bearing particles. We can also diffusion bond these materials together, as I mentioned, from the phase diagram. They do have some solid solubility in each other, and so that allows us to diffusion bond them. You can barely make out an interface shown there. We do this typically around 14 to 1600 C diffusion bonding, but it does diffusion bond quite nicely because of that solid solubility. So why are we doing this from an application standpoint? Well, because the ZRC tungsten does have a much higher failure strength, what that allows you to do is to make the plates much thinner, actually, for the stresses that are applied, say, with high-pressure supercritical CO2 in a heat exchanger. And so this is an initial calculation done for us by Sandeep Pitapparti and Devesh Ranjan, Professor Ranjan at Georgia Tech. Ashay's group has been continuing to do some of these types of calculations for us with modified geometries. And so because the metal alloys do not have as high a failure strength, they need to be made thicker, the plates, which then means that the power density, the megawatts of heat per cubic meter, is only much lower. It's less than typically about 4 megawatts per cubic meter for a particular 10 megawatt electric heat exchanger in this calculation. for the same type of heat exchanger, depending on what you pick as the factor of safety for the ZRC tungsten relative to its mean fracture strength at 800 C of 600 MPa, you get on the order of 9 to over 10 megawatts per cubic meter calculated power density for this material. And so that's the big attraction. We can make heat exchangers not only at lower cost potentially, I'll talk about that shortly, with higher performance, but with higher power density. So we're currently in the process of fabricating headers and bonding them to stacks of diffusion bonded ZRC tungsten-based heat exchanger plates for pressure testing. We're also evaluating other scalable manufacturing methods for making larger area plates. And also we've been working with the Henry Group on techno-economic analyses for scaling up this process. So in terms of making large area thin sheets, a standard industrial way to do that, in the electronics industry in particular, is tape casting. You can make large areas, sheets of ceramic organic mixtures. Of course, to do that with tungsten carbide, we need to have a slip, a suspension comprised of the right dispersant, binder, plasticizer, and solvent. The idea is you pour that ceramic slip into a reservoir that flows underneath a gap under a doctor blade that defines the thickness of the tape, and the solvent evaporates off, and you can make, this way, very formable sheet. And so Ashay's group has done a really nice job of evaluating that in detail. And so they looked at a scaled up 2.83 meter by 0.6 meter by 1.25 meter tall heat exchanger made of 1.5 millimeter thick plates. They looked at the raw materials cost, which is tungsten carbide powder, zirconium, and copper from the liquid. That turns out to be about, for this heat exchanger, about 3.7 cents per watt or $27 per kilogram. We worked with Ashay's group to lay out a manufacturing plant at the production rate of 100 plates per day, with facilities for powder handling, plate forming, sintering, melt infiltration, bonding, etc. Professor Henry then used a Ricardo model, which is an Excel spreadsheet model inherited from the automotive industry, with incredible detail on costs, raw material scrap, equipment, labor, energy insurance, property overhead, property tax overhead, and much more than I'm saying here to cover the processing cost. And what they discovered was that a production rate of 10,000 plates per year, which for this heat exchanger corresponds to about 13 heat exchangers per year, the processing cost drops to about 15% of the raw material cost for an overall cost of about 4.3 cents per watt, which compares very favorably to nickel-based superalloys, which don't have the properties that these materials have, made by the conventional etching process, and we think even favorably to stainless steel etched heat exchanger plates. Again, they don't have the properties that our material has. So that's kind of a quick example with that process. Let me quickly go over a second example for reaction, which is the gas-solid reaction approach. One of our favorite templates to play with are diatoms. Diatoms, if you're not familiar, are single-celled algae found all over Earth, from the Arctic to the equator. Both marine and freshwater diatoms exist. They are the most populous of the microalgae in the ocean. Something like 40% of the eukaryotic phytoplankton are diatoms. I think even more impressive is 25% of the primary biomass. All the plants on Earth, 25% of the biomass is in diatoms. They're that prevalent. From our standpoint, they're quite interesting because they form rigid cell walls called frustules made of specific types of organic macromolecules and silica. And so they make incredibly intricate silica structures. This is a collage of SEM images, scanning ultra microscope images from this book called The Diatoms, a really great read. And it shows just a small number of all of the diatoms that exist, how varied and complicated the shapes can be, from disc shapes with pores that get smaller as they spiral inward, to cylinder shapes, to almost inverse opal-like structures, spiky shapes, even overlapping hinges type structures. A remarkable shape-forming ability by these organisms. They truly are nature's nanotechnologists. There's something like 100,000 species thought to exist on Earth, each of which is genetically predisposed to make a particular shape, and it makes that same shape over and over again upon reproduction. Such that, for example, if you had 80 reproduction cycles, 80 doublings, if you type that in your calculator, that's more than a trillion of the same three-dimensional shape. Incredibly, massively parallel self-assembly. But these are made of silica, and while there have been valiant efforts made to modify diatoms to form other materials, that's largely failed. And so that's where we come in. We've developed a process that we call a basic biological assembly, use nature to make the large numbers of the complicated shapes, and then use our techniques to change the chemistry but not the shape. And so we've done this with diatoms because they can make large numbers by repeated replication. And as I show you schematically here, we can then change the chemistry, but not the shape and even the nanoscale features. So one of our diatoms I work with quite a bit is called Alchemy. It, like all diatoms, has two halves to its frustal. On the right, you see an image with two halves with overlapping finger-like extensions. It's a cylinder with nanoscale pores that run, submicron scale pores that run along the cell wall length. So what I'll show you next is a collage of images, either half or a complete frustal that we converted over the years into a variety of other materials. So that includes converting the silica into magnesia, into zirconia, into titania, for a host of electronic or sensor applications, into europium-doped barium titanate, which is a red glowing phosphor particle, manganese-doped zinc silicate, which is a green glowing phosphor particle. We made blue glowing phosphor particles as well in almost any shape you want now because of the diatom of shape availability. We made elemental replicas, gold, platinum, palladium, copper, nickel, silver, for a number of applications. I'll talk about some of those. We made porous silicon replicas of relatively high surface area and carbon replicas of even higher surface area, carbides, and even organic replicas. So I'm not going to go through all these, but I'll emphasize today one example, and that's silicon. So if you're interested in doing this type of work, you can obtain diatom cultures from a number of places, including the Professor Guillard Center in Maine. That's been a great source for us. For a modest amount, you can buy a test tube with your favorite diatom species. We have a diatom culturing chamber in my group, and we culture them in ever larger containers. You can see it's a yellow-green type algae. We've gone up to actually 200 liters in some cases. And this is in a chamber with controlled temperature, controlled lighting conditions to mimic nature. So we harvest them in a centrifuge, and then we burn away the organic, and we can see by X-ray refraction we have silica here. In this case, to make silicon, we use a reducing agent, magnesium vapor. So magnesium gas can react with silica to form magnesium oxide, and silicon, again, a displacement reaction. The oxygen is displaced from silica to magnesia. That gives you a product with about 65% by volume MgO and 35% silicon. By X-ray diffraction, we can do this at quite low temperatures. Magnesium is a very effective reducing agent, and you can see quite broad peaks for MgO and silicon. Because it turns out that in this case, at these temperatures, we get a co-continuous mixture of MgO and silicon. You can dissolve either phase away and maintain the structure, albeit porous. Here's a cross-section of the TEM of a typical nanostructure of these materials, very nanostructured mixture of MgO and silicon. And so we dissolve the magnesium oxide away in a dilute acid. Magnesium oxide is a very basic ceramic. So we can go from silica to porous silicon because of the volume reduction that happens in this process, typically about 56 or 59% or so. And in doing so, we can generate an all-silicon replica. Again, the peaks are quite broad. If you use a simple shear analysis, it gives you an average grain size, crystal size of about 8 nanometers, which is confirmed by TEM as well. So here is an example of an Alchemy frustal converted completely into porous silicon by this process, with a surface area of over 500 square meters per gram. It turns out much of this porosity is what's called microporosity. If you plot the pore volume versus pore size, much of it's below 2 nanometers, which is considered a in the porosity field microporosity. We've done this with other diatoms. Here's a diatom called Coscona discus Reilly. It's a disc-shaped diatom that has this rather intricate pore structure. So on the left, you see the overall image of the diatom and the EDX pattern showing that it is silica. The same frustal in the middle, now converted to MgO silicon, and on the right, to silicon by dissolving the MgO away. We made a higher mag image of the valve. You can zoom in. You can see the same 7 large pores are there, pretty preserved at each stage. If you zoom even further, you can see 3 larger pores with smaller pores beneath it, preserved at each stage. If you zoom in even further, you can see even finer, the higher resolution of those pores below. And if you zoom in even further, the red circles are the same of big pore, the yellow circles are the same. Even if you look at the yellow circles, even the fine structure beneath the fine pores in the big pore are preserved. So we can get preservation down to the on the order of several tens of nanometers resolution with this process. So you might ask, well, what's it good for? Well, porous silicon has a number of applications, not the least of which is as anodes potentially for lithium-ion batteries. We've worked quite a bit on this with colleagues. Others have as well since we published this first. It can be used as an inverse opal material for infrared applications or metamaterials, photoluminescence. Porous silicon has that characteristic. High sensitivity sensors, which I'll talk briefly about, as a catalytic substrate, photocatalytic substrate. Since we first reported this technique back in 2007, we were happy to see that it's been adopted by a number of groups. It's been now cited over 9,800 times, the technique. you do a Web of Science search for magnesiothermic reduction silicon, since our first paper in 2007, it's taken off. And so this has become a fairly common method for making porous silicon for a number of applications, but not the least of which is as an anode material for batteries, for lithium-ion batteries. So we're happy to see that it's helpful to other people. We've also been doing this with Zihao Bao's group at Tongji University in Shanghai. This is the SIO powder that was made basically into Swiss cheese silicon, as you can see here in the transmission electron microscope image, and he found that the capacity of the anode was well preserved because of the porosity and nanoscale nature of the silicon over a number of cycles this way. We've also applied this method to synthetic silicas. We've been working with Joanna Eisenberg's group at Harvard. She's got a very nice technique for making large area, defect-free silica inverse opals, as you can see here. We've converted those into silicon inverse opals for infrared applications or titanium inverse opals using a different displacement reaction involving a chloride vapor as well for optical applications. Let me spend a little bit of time quickly talking about a sensor application we collaborated on with Professor Adibi's group, Ali Adibi at Georgia Tech. The idea here is to use a racetrack resonator. So you can launch infrared light down a silicon straight waveguide. For particular wavelengths, the evanescent field of that light will couple with a nearby racetrack that has a particular spacing. And so when that happens, you get a dramatic reduction in transmission along the waveguide, and that happens at very particular wavelengths. So if you happen to have a porous silicon surface on a dense silicon racetrack or waveguide, that provides more surface area for an analyte to attach. And when the analyte does attach, that slightly alters the refractive index contrast, which shifts the wavelength at which this sudden reduction in transmission occurs. And so you can use it as a very sensitive detector. So we took silicon on insulator, silicon layer on silica on a bulk silicon wafer, partially oxidized that upper silicon, and then ran our magnesiothermic reaction to form ultimately porous silicon on dense silicon. There is a catch, though, in doing this. The top reaction you've seen already, that's the displacement reaction. The bottom reaction can also occur under the right conditions. The silicon can continue reacting with magnesium to form a phase that you don't want for this particular application, magnesium silicide, as you can see from the phase diagram here, the magnesium silicon phase diagram. So to get around that, we examine the partial pressures of magnesium required for both reactions to happen thermodynamically. So the top reaction is quite low, 1.4 times 10 to the minus 10 atmospheres. For the bottom reaction, it's quite a bit higher. So what that means is if you're below the 4.1 times 10 to the minus 4, but above 1.4 times 10 to the minus 10, you can get the top reaction to happen, but not the bottom one, the reaction 2. A simple way to do this is to take magnesium silicide itself as the gas source. If you heat it up, it will have a partial pressure of magnesium. It will have no desire to reform magnesium silicide, and that magnesium vapor pressure is more than enough to react with silica selectively to form silicon and not magnesium silicide. So that's what we did. And the top X-ray pattern you see on the left here has the mixture of two phases. We dissolved the MgO away. And you can see on the right the very nice conformal, uniform thickness, highly porous silicon layer we put on silicon. So then the Adibi group patterned this lithographically. Here's a top-down view showing the racetrack and the nearby linear waveguide. If you zoom in, you can see the porous and a cross-section of porous silicon on top of the dense silicon that we made, and the top-down view of the waveguide and the resonator. So the Adibi group then measured the decline in transmission at particular wavelengths without the porous silicon layer on top. You can see that here, many decibels decline. If you zoom in on one of these, the 1551 nanometer peak, you can see the peak here has a Q factor of about 24,000. They put aminopropyl triethoxysilane on that solid surface, shifted as you expect from the change in refractive index contrast a little bit, and then added NHS biotin, which covalently bonded to the aptes, and that shifted a little bit more. When we put porous silicon with our process on the resonator, again, you have these massive drops in transmission at particular wavelengths, but now the shift that happens when you put the analyte on is about a factor of 6 higher, and we don't substantially lose the quality factor. And so this is a really nice way to make porous silicon on dense silicon for optical detection applications. Let me quickly talk about the other coding techniques. I won't spend as much time on these. One of our favorite templates biologically is pollen. Pollen particles are used to transfer, of course, male genetic material across plants. There are different types of pollen that are wind-based, airborne, entomophilous pollen, or insect-borne, entomophilous pollen. There's a variety, again, of species-specific shapes that exist among pollen grains. We've focused on sunflower pollen, which is circular or oval in shape, has these spiky features called echini. That pollen can adhere by entanglement, say with the hairs on bees' legs, by van der Waals attraction from the spikes that you saw there. And there's actually a fluid called pollen kit that's quite sticky. The pollen exon, the outer layer, consists of sporopollen, which is a robust polymer that's rich in carboxylic acids, that is to say hydroxyl groups. So we utilize a technique invented by Kunitaki's group in Japan called surface cell gel processing. The idea is you take a hydroxylated surface like a pollen particle, expose it to a metal alkoxide like iron isopropoxide, for example. One or two of the alkoxide groups will react with one or two hydroxyls, liberate alcohols and form a metal oxygen bond, and that will continue until you form a monolayer. The unreacted alkoxides that are dangling on the outside can be re-exposed to water to form hydroxyls, and this process can be repeated. Alkoxide, water, and layer by layer build up the desired material, and then burn away. You can burn away the underlying material to make a replica. So one of my students, Phil Brook, a very clever student, developed an automated process for doing this. To put many layers down. So we put the pollen over a porous ceramic frit, turn a computer on, pump in alkoxide for a certain time, then wash away the unreacted alkoxide excess, introduce water to rehydroxylate the dangling alkoxides, and then dry, and we can do this over and over again. Turn it on, come back the next morning, and have hundreds or thousands of layers. And so what you see here on the left is a pollen particle again, sunflower pollen. On the right is after 30 surface cell gel cycles with iron isopropoxide. It's a very conformal coating. If you take that and fire it in a TGA, you get different amounts of weight loss, of course, depending on how much of a layer you put on, 10 or 50 cycles. On the left, you see again the iron oxide coated pollen. I've pointed a red arrow to show a cracked akini and a green arrow to show a ball on the end of one. On the right, you see the same pollen particle now as hematite after firing, and again you see the cracked the akini and the one with the ball on the bottom, on the outside surface. This is made of hematite, which is weakly ferromagnetic. We wanted to make a stronger magnetic material, magnetite. So we borrowed a trick inherited from Fred Rhines, metallurgy trick called Rhines pack. We take Fe2O3 pollen particles, put it in an iron ampule along with an excess of magnetite and iron, heat it up to 550 C. The excess magnetite and iron establishes an oxygen partial pressure that will allow for only the formation of magnetite from hematite. And so that's what we did. And so we generated a magnetite pollen replica. As you can see from the X-ray diffraction, you can see it from the EDX iron. We collaborated further with the Meredith group at Georgia Tech. They have a really nice way of measuring adhesion. So we took a native pollen particle as well as a magnetite replica. Carson's group then stuck it onto a permanent magnet and then pulled it off to see what the adhesion modification was. So this is a plot of force versus distance. Actually, two length scales. On the left is the nanoscale, on the right is the more micro scale. If we put the magnetic pollen particle on silicon, which is not magnetic, you do get van der Waals type adhesion that pulls off the sample at the low range. If you put the magnetic particle in the center of the permanent magnet disk, where there isn't much of a strong field, again, you get the short range order only. But if you put the pollen particle on the cantilever on the edge of the permanent magnet where the field is much stronger, not only do you get the short range adhesion, but you also get long range adhesion due to the magnetic nature of the replica, out to about 1 millimeter. And in fact, of course, if you put more of the magnetite on by having thicker layers, you get more of a long-range effect as well in terms of the force applied. Okay, and then very quickly, let me show you how we can make metal replicas as well. Again, we go back to our diatoms, which contain a native amount of hydroxyl groups on the surface. We did this with Seth Marder's group at Georgia Tech. You can take an alkoxide like a 3-aminopropyl triethoxysilane, react it with hydroxyl, and then put amines on the surface, covalently bonded. Those amines can act as sites to bind catalyst particles that will allow for electroless metal deposition. So we did that. Here you see a copper coating on a diatom. Admittedly, not a great coating, however. It's not very conformal, as you can see on the right. So when you dissolve the silica away, it falls apart. So we knew what we had to do was to have a much higher loading of catalyst to get a much more conformal coating. So we worked with the Marder group. They came up with a really nice approach for this. You again can put amines on the surface through the silanization process I just mentioned, but you can amplify those amines. And so the idea is to take a multi-acrylate molecule like erythritol pentahexaacrylate with 5 or 6 acrylate groups. Any one of those can react with the amines to covalently bond. And the remaining 5 or so acrylate groups can react with a polyamine like trisaminoethylamine. Any one of the amines can react with any of the acrylates. And you can go back and forth between acrylate amine, and really dramatically amplify the amine density on the surface to capture more catalyst to get a better coating. So here, in fact, is a copper replica. The silica has already been dissolved away through pinholes occasionally in the coating, and you can see you get a very nice replica, negative replica of the diatom. This shows EDX that there is no more silica left going through the coating. We've done this also with custom discus austeropolis for a particular optical application I'll mention quickly here. This particular diatom frustal has pores that are about a micron or so in diameter. And so we made a gold replica. This is actually a gold-coated sample the same way. You can see on the left the EDX pattern showing silica as well as the gold coating, and the X-ray photoelectron spectroscopy analysis, which is the surface that shows the gold present. We then dissolved the silica through occasional pinholes in the coating. This is an all-gold replica of the starting frustal. Now there's no more silica left from EDX analysis. So why did we do this? Well, it turns out we wanted to investigate a phenomenon called extraordinary optical transmission. If you have a plasmonic material like gold, if you have pore channels that have a certain spacing and you launch a certain wavelength of light, you can generate surface plasmons that will radiate out from those pore channels. If the pores are properly spaced, you can get a standing wave that will amplify, detect the bottom, and scatter off the bottom, so that you can get transmission through a porous material where the wavelength transmitted is larger than the diameter of the pores. Hence, it's called extraordinary optical transmission. So here's an example of a gold diatom replica we made this way with pores that are about a micron or so in diameter. And we checked to see if we could transmit infrared light of a larger wavelength through this. Now, because the pores are not the same wavelength, you actually get because the pore spacing is not the same exactly, you can actually transmit a range of wavelengths through this material. And in fact, it works. This is with Joe Perry's group at Georgia Tech. You can see you get an enhancement in transmission at about peaking at about 4.3 microns through this material. So this is a potential material that we could use by putting on detector molecules and detecting shifts in transmission for sensing applications. So quickly then, I hope I've convinced you that we can take shape-preserving liquid solid or gas solid reactions, take synthetic or biogenic templates and convert them into CRC tungsten, for example, or porous silicon replicas, and many others too. We can take microscale organic or bioorganic structures like pollen grains or butterfly scales and use conformal coding techniques like surface solid gel to deposit a wide range of ceramic chemistries and then fire them to make replicas. I didn't mention the metal coatings that we can do as you've seen as well. And so why do this? Well, you can generate 2D or 3D synthetic or biogenic structures for a number of applications, including very important thermal ones like solid fuel rocket nozzles or heat exchangers. We've also been working with the Henry group, I didn't talk about this, on pumps for CSP, for pumping molten salts, also for engine components, high surface area electrodes, as I mentioned, for batteries, but also for fuel cells. We didn't get into it. We've also made high surface area materials for absorption purposes, like removing arsenic from water, optical structures for tailored transmission or reflection for sensing or anti-counterfeiting, and tailored adhesion, as I showed with endowing pollen particles with magnetic characteristics. So let me acknowledge the financial support from the Department of Energy, the Office of Energy Efficiency and Renewable Energy, the Solar Energy Technology Office has been really wonderful in terms of providing support and help, and technically as well in the work of the Office of Basic Energy Science, Department of Energy, Biomolecular Materials Program, and some of the diatom work, as well as the Air Force for diatom work, as well as on rocket nozzles, the Navy on some of the Muri stuff we've been doing, including a Muri shown below there, led by the Eisenberg group at Harvard called BioPaints, Bio-enabled particle adherence for interrogative spectroscopy, where we looked at pollen particles. And so with that, I'm happy to take any questions or suggestions that you might have. Thanks for listening today.
Thank you so much, Ken. Great talk. Please, if you've got questions that you want to ask Ken, please go ahead and put them in the Q&A box. I'll start off with a couple questions of my own. In looking at this work, I was really intrigued by the diatom portion. I was curious, have you ever thought about maybe converting diatom shapes to make the starting particles for the DCP process? So like, could you, for example, make diatoms or use diatom shapes to maybe make an oxide or a carbide, and then use that to possibly be mixed into the powder that you use for DCP to then possibly get some really interesting, unique mechanical properties? Because now you got like, oddly shaped pieces of metal that are particularly inside the material now that would enhance the properties. You would be able to get the microstructures that you wouldn't be able to get any other way. You ever thought about doing something like that?
Thought about it, but haven't done it, actually. So that's a really great point, Ash, because to your point, I mean, for example, in the ZRC tungsten Ceramet case, I suspect, and you and I have talked about this actually in the past too, that that the mechanical behavior could be substantially affected by the microstructure we have. But we're already getting pretty decent properties. You know, room temperature, fracture strengths of average of 700 MPa, a significant fraction of a gigapascal. But I think we can do even better, to your point, by engineering the starting because that process. It's a really good question you're asking, because the DCP process is one for which the morphology of the tungsten carbide you start with is the morphology of the tungsten and to some degree the DRC that you inherit in the final product, because you get a layered morphology that thickens over time. And so if we take a fibrous-like or a cylindrical-like aspected shape, and we have made carbides out of the diatoms. We haven't made tungsten carbide replicas of the diatoms, but I think we could. We made tungsten carbide replicas of other particles, actually, but I think we could do that. And then to your point, make a macroscopic. So I think what you're getting at, which is an interesting idea, is hierarchical structure control, right? Yeah. Where you can control down to the nano, to the micro, and the macro scale by 3D printing, right? And I think with this process, with these set of processes, we have the ability to do that, actually, by taking advantage of preformed materials. Again, divorcing shape from chemistry, right? We can start with a preformed material that has the shape we want. From the nano to the micro scale, we can pattern it to the macro scale with 3D printing, and then convert it to alter the chemistry the way we want. So I think you're making an excellent point as a really elegant way, in a very controlled way, at every size scale, controlling the structure and the phase distribution we wind up with. It's a good question. We haven't done it yet, but I think it's an interesting area to consider for sure.
Yeah. So what are out of curiosity, what are the different carbides you've managed to make on the diatoms?
So far, just silicon carbide, and that was because it was an offshoot of the silicon, right? We took the silicon replica we made, we carburized it afterwards to make silicon carbide. And actually, we took that and removed the silicon to make carbon replicas. That's how we made the high surface area carbon replicas we made. So yeah, we've done, only because it was kind of a natural segue from the silicon work that we had done earlier. So that's what we've done so far, just silicon carbide.
Interesting.
But I think there are chemistries that could allow us, gas phase type chemistries that could allow us to convert carbon into tungsten carbide.
Interesting.
I haven't done it, but I think it could be done.
Another question I have is with regards to there's some applications like hydrogen storage where people are interested in reversible absorption of hydrogen back and forth. Have you ever thought of using these kinds of approaches to make materials that would facilitate the transport of getting hydrogen, for example, in and out of a hydrogen storage material? So you can maybe make something that's pretty dense, but has pathways to get the hydrogen in and out, and it can accommodate the volume change.
Right, and so we have made. So one of the, I didn't get into this, but one of the more recent things we've done is to take diatom silica and through a series of reactions convert it into porous but shape-preserved titanium. Actually, we did that for an RPE project for lightweighting because titanium itself is lightweight, and the diatom structure is inherently strong. I didn't get into this, but at least one of the reasons why the diatoms make their silica shells is to survive attack from other organisms in nature. So they make the shells incredibly tough with their architecture. So we thought, why not make a tough material into something that's inherently even tougher, titanium? So to answer your point, we made porous titanium diatom replicas. And one of the challenges, funny enough, though, is that it's hard to. At one stage, we formed titania, and then we converted it to titanium, and there's some hydrogen involved, so it's hard to avoid forming a hydride. So those are fairly high surface area metal replicas that are very easily formed as hydrides. Now, I'm not up to date enough to know what the preferred hydride materials are for those types of applications, but I think it's very possible to make, porous materials that have, macroporous for getting the gas in and out, microporous for high surface area for generating, high density of hydrides. And I think to your point, and again, and kind of back to your original question, you can architecture the material from the nano to the macro scale, with the right particles, with the right, conversion process, to engineer fast pathways. I mean, in some ways, I guess it's like a battery, right, where you need highways to get the lithium in quickly.
Exactly.
But you need high surface area to capture a lot of the lithium. Same idea for that. You want to have highways to get the hydrogen in and capture a lot of it at the same time.
Mm-hmm.
Yeah, I think you're right. That's another way to do it.
Yeah, with hydrogen getting more attention now, making a comeback, it might be interesting to think about that kind of approach. One of the questions from the audience we got is about the thermal cycling and of heat exchangers. I know that you moved through it rather quickly. Do you maybe want to talk a little bit more about any actual testing you've done in terms of how mechanical properties or survivability of the joints and things like that over thermal cycles? How any data you have to support that actually works?
Right. So what we did an ASTM bend test at room temperature at 800 C and at 800 C after thermal cycling. And what we found was there was no degradation after. So thermal cycling was conducted at 10 degrees a minute up to 800, from room temperature to 800 C and back down again. And we did that 10 times. And we measured 10 fracture strengths with 10 samples under each condition: room temperature, 800 C, 800 C with cycling, so 30 samples. And we saw no degradation in mechanical strength, the mean fracture strength of the samples. Another good question you're asking is about interfaces. We have actually in a current project, not with that composite, with another one, a plan to bond them together and then cycle them. For the ZRC tungsten, we've certainly done diffusion bonding. I don't remember that we've actually done mechanical tests. But there are mechanical tests that one can conduct where you have sort of a bonded interface and you try to shear it. And actually, we did do that with some interlayers and came up with I have to go back and look at my notes to remember exactly what we did in terms of what those were. But we did come up with strategies that would allow for effective bonding by a shearing type mechanism after a thermal cycling. And so one can play tricks like that. Certainly direct diffusion bonding with ZRC tungsten to itself, or if you want to do it, I mean, typically, as I mentioned, when you do the direct bonding with ZRC tungsten, you have to go to 14 to 1600 C to get that to happen, to get the diffusion to happen enough. If you put an interlayer in between that will react, you can do it at lower temperatures. And we did do that. I just don't remember exactly off the top of my head. I have to look back in my notes to remember. It's been a few years since we did that. And we did a shear test to meet the objectives that we needed for doing that. So to answer the questioner's point, it's a good question. And certainly for joints, one has to be concerned about the conditions that you used to do the joining, any new materials you put in there, and then the cycling that results. But certainly for ZRC tungsten by itself, we've done extreme thermal shock with the Pi-K rocket test and more moderate thermal cycling test at 10 degrees up and down 10 times, and then tested before cycling and after cycling at 800 C.
Yeah, another question on the DCP line of thinking is really about cost. And so, you say zirconium carbide, tungsten. I mean, most people have never seen or let alone held zirconium carbide in their hand. So it kind of sounds a bit exotic. What have you done with regards to, I guess, reducing uncertainty around what the costs would be? There were some intriguing numbers you showed in terms of cost per watt. Can you talk a bit more about how the cost of these things might make it feasible or competitive in different contexts with regards to like the existing state of the art?
Okay, so for heat exchangers as an example, the common way to make currently a printed circuit heat exchanger is an etching process. So you take a sheet, you pattern it, you have an organic layer on top, you sensitize the organic in a certain pattern, you remove it in that pattern, then you etch. That's a fairly slow process because you have to get rid of all the material. Obviously, stainless steels, nickel alloys have a number of components in them, and you got to get rid of all of them in that space where you're trying to make a channel. In our case, we avoid that completely. So in addition to the cost, which I'll talk about in a second here, we also can make channels that are different than what you can get by etching. Typically, when you etch a channel, you get a channel that's wider than it is deep, right? Just by the nature of the etching process. In our case, we don't have to have that. We can have rectangular channels if we wanted to, or channels that are deeper than they are wide, actually, because we can generate them by forming. And so yeah, from a cost standpoint, That's a good question. We're particularly going after techniques that are known to be scalable and known to be cost-effective in industry. And so we avoid hot pressing, we avoid sintering because of the distortions and the low yields that you get from distortions, and we focus on things that are relatively cheap to do. So simply pressing of a preform with binder in a targeted shape and then removing the binder, slip casting, gel casting, tape casting, all processes that are known to be scalable. Now, mind you, any one of those processes you have to tailor for a particular material, like tungsten carbide, for example. So it's not like you would, on day one, you're going to have it all figured out. You have to work through the processes, work through the techniques, work through the compositions you need, besides tungsten carbide, to get it to be effective and reproducible. But we particularly target those techniques because they're known to be scalable, known to be cost-effective. Then we avoid the sintering shrinkage. We avoid the distortions that can happen by using our reactive melt infiltration process. Melt infiltration is not a new thing. I mean, in fact, General Electric and Rolls-Royce and a number of companies are looking at silicon carbide composites, for example, for jet engines. Now, to their credit, General Electric has been at this for a long time, actually decades. And in their LEAP engine, they've now got components that are silicon carbide based, fiber reinforced, with a matrix made by melt infiltration. And so, mind you, that's a pretty high-end application, at turbine components, but it's not one that's foreign to industry, right? So melt infiltration techniques are certainly known techniques, and we're pursuing that to overcome a common ceramic problem, a common problem with ceramic-rich composites, which is distortion and low yield upon sintering.
So just as a quick follow-up, how does the cost compare if you account for, as you mentioned, higher or potentially higher processing costs to actually make the shape in a case of a metal like stainless steel or nickel for the heat exchangers as an example, to maybe more expensive material but simpler forming process? How does it work out overall in the end when you add the two together? I mean, at the end of the day, you want a part, so you have to pay for the material and the process to make it. How does it compare to the state of the art in that respect?
Yeah, so that's a good question. I mean, so if you break it down into the raw materials and then the processing cost, the raw materials cost in the case of ZFC tungsten as an example, tungsten carbide and copper and zirconium. I looked at this actually, and I both looked at this. If you look at the basic materials that comprise nickel-based superalloys, like Inconel 740H or Haynes 230, and you just look at the top four elements that are in each of those, and you look at the geological survey or the scaled up cost of those raw materials. The raw materials costs for ZRC tungsten were very similar to nickel-based alloys, right? Just starting the minerals that are used to make those metals, right? But in the case of the heat exchangers, you have to form the plate in the first place by metallurgical techniques, and then you have to etch the plates. And so, because we don't have to etch the plates, I think scaled up, our processing costs can be quite a bit lower. And our raw materials costs, the tungsten carbide scaled up, the copper and the zirconium needed, are very similar to what the raw materials costs were for the top elements and the nickel-based superalloys. So, yeah, I do realize it sounds exotic, but if you look at the raw materials costs scaled up and the processes that have been developed, I think we have a good chance to be cost-effective. We're a little bit behind because obviously nickel-based superalloys have been around for jet engines since World War II. Sure. So we don't have the decades of experience that the really smart metallurgists have had in developing those really excellent materials, the superalloys for jet engines. Mm-hmm. But I think there's a potential with these materials to exceed in particular applications, not everyone, but in particular applications, the performance of those alloys. Right now, they're being pushed to their limit. Nickel-based superalloys and turbine blades are getting, you kind of have to do extra things. You got to put a thermal barrier coating on the outside. You got to cool from the inside, just to be able to use these materials because they're approaching their solidus temperatures, which is as much as you can really ask a material to go through. I mean, if you're going to push it to its limit temperature-wise. So I think we're at a point now where we have to come up with better materials if we're going to really go beyond what the ultimate limit's going to be for nickel-based superalloys.
Yeah. One last question before we wrap up. Have you thought about utilizing the structures you can make with the diatoms as like gap separators for nanoscale applications? Like if you could have a reproducible gap size using those kinds of structures, or have you thought of using them at all in kind of fundamental experiments that people want to do where they want to test something, but it's a really difficult test to do and you need a very small gap, or you need certain structures to enable the experiment itself?
Good question. So diatoms make very elegant, intricate structures, but for likely reasons for survival, the spacings are not identical every time. I mean, for example, in the Cosconodiscus bilesii diatom I was showing you, the pores aren't exactly the same size, the spacings aren't exactly the same. So it depends on how precise you need those dimensions to be. I mean, certainly there's excellent research and development that's been done with silica. You can make, by cell gel techniques or other techniques, silica layers that are very controlled in thickness, right? And then if you want to convert that into something other than silica for chemical reasons or for temperature limit reasons, then you can use techniques that we've developed to do that. And if you run those types of reactions or coating methods properly, you can control the morphology and not have it fall apart in the reaction process. So if you push me again, really force me to say, hey, how can you make something that's a few nanometers thick reproducibly? I wouldn't go to a diatom to do it. But there are certainly synthetic techniques. I mean, what was nice for us about the diatoms is they're complicated shapes, and we could easily test the shape preservation of a complicated shape, by our techniques because they are so complicated. But we can just as easily then transfer that knowledge from converting silica, biogenic silica, to synthetic silica. And that's what we did as an example with the Eisenberg group. They made very nice inverse opals. We knew how to convert them, so we tried it on those after we did it with diatoms. And so I think it's a good question the listener's asking. If you have a particular application where you need a shape, you need a dimension, you need a chemistry, you kind of have to look at all three aspects of it. And because we can divorce all those steps from each other, you can pick the best way to make a given thickness, you can pick the best starting chemistry, and you can pick the best conversion chemistry to make a gapped material exactly the way you want it. You have the ability to engineer all three of those processes to get exactly what you want in the end.
Yeah, very nice. Very fascinating work. Thank you again so much for giving us a talk today. It was really, really fascinating and interesting work. I'll just remind everyone, our next webinar is on fusion reactor first wall cooling from Professor Dennis White. And if you have not already, please sign up for updates and reminders on inotherm.mit.edu and give us your suggestions for future events. So with that, we'll end our session here today, and thank you all for attending.